Okay, so last time we have implemented the toBin function in our BigInt class. So now what we should do is we should implement the fromBin function, which will take a binary string and then convert it into our binary representation. So any volunteers who would like to implement that? Well, since there is no one offering to do it voluntarily, let's pick someone. How about Mr. Leonardo?
Sure, can you give me one moment just to switch computers?
Mm-hmm.
There we go. I'm gonna need some help connecting to the
Okay.
um,
So the IP
session.
should be the same as last time. Let's quickly check that. Interesting. That takes longer than usual to check the IP. Let's do it differently. So that's the IP address. Where's the chat window? Here's the chat window. And I think the password was, I think this one. Wait, one more thing. We need the right port. You don't need to just enter the IP, you need to enter the IP and then the port, which was I think 6900, but let me quickly check that. Whether it's the one we have selected. 6900, yes. So with this, the lower string should connect through the VNC viewer to the virtual machine, and then I think the password is correct. If not, then I will change it once again. That's luckily easy enough to do.
Okay, a moment. I don't exactly remember how to connect it through the
Do you have
program.
the VNC viewer?
I don't.
Okay, then let me find the download link for you. There are quite a few VNC viewers, but a good one and the free one is the Ultra VNC viewer. So there is a download for Windows as a zip as well, so we don't need to install anything. Let's see if we can find the best. It's the newest one. I don't want the installer, I want the binary. Should be this one. I think the download should be on this page. Once it counts down the countdown, and then from inside, when you unpack it, you should get this content. And then if you go into the x64 folder, use the VNC viewer exit to connect to the server here. I would recommend everyone to download the viewer just so that for the next time it might be your turn that you already have it running.
Yep. Authentication rejected. Let me try again.
Should be working. Let me quickly try. No, it's not working. That is not good.
Did you get any message on your side? Or
no.
did I try to connect?
I'll try again from another test system. Now that should be working.
Okay, there you go. Now it opens.
Perfect.
Okay.
Okay, so as said, we get a string. With hexadecimal notation, it is often very often customary to prefix it with 0x. With the binary notation, if you write in theory a binary string in C++, you start with 0b, but that is something that is more C++ specific. It's not like a thing that you would usually expect when handling with binary strings. So in this case, we don't need to check for any prefixes. Unlike as with the homework assignment, and here we can just directly start passing the string and pushing the individual bits into our data block. Do you want to start on your own, or shall I give you a rough outline how to implement the function?
I mean, I know how to iterate the data, but I'm not sure if I know exactly how to translate it from binary to like a number or a string at the top of my head. So yeah, iteration should be basically the same from what we did last week. So the same here.
Well, it's kind of the reverse thing. It's the reverse thing.
Yeah, we could start because then you can use pushback, right?
We don't have a pushback on our binary data since it's just an array of chunks. But the recommended way of starting it would be first to count the bits inside our input string, then round it up to the next full size of something round it up to the next full size, what would fit in our data block, and then allocating, of course, this data so that we have a place to put the new string into, because as we start with a newly created big int, it will not have any m pointer p data allocated yet. So we need to do that. And once we have allocated this, you can make one loop that goes through every character in the string, checks whether it's 0 or 1, or if it is something else, then just bugs out with returning an error because other characters are not valid. And if it's 0, since we usually initialize everything to 0, you don't need to do anything. And if it's 1, then you need to write 1 to the right position in the pdata array. So to write the right position, you need to first calculate in which chunk the bit is located, and then the right bit offset inside the chunk, and then you can set it.
Okay. I don't think I'm gonna be able to do this during the time period of the class.
Well, we can try it. I don't think it's so difficult. First thing to do, as said, is to get the length of our value. So we'll just make an array, call it size or something, a variable, call it size, and then just assign to it the length of the string that we have in front of us.
Yeah, one moment. Sorry, it's been a while since I did any C++.
To create a variable, you write the type you want it to have, and then the name you want it to be named, and then you can assign something to it.
But for an array for this size?
No, just a normal variable, not an array, just a variable of, for example, type size t, or int is also fine, and then you call it bit count or something like that. Almost right. Bit count, not byte count.
Oh.
And then you can assign to it the return value of values. Size of will not work. Size of gives you only the size of machine types. What you want is you want to call the function length on our value object. So you just write value dot size or length. If I remember correctly, it should have both. You need to, since it's a function, close it with opening and closing brackets, even though you don't provide any arguments. Okay, now we have the count of bits. So the next thing to do is to figure out how many chunks we will need to accommodate all those bits.
So we have the big-int chunk, and I guess we just divide big-int chunk by this value?
Well, big-int chunk is in bytes. So if you take size of big-int chunk, then you get the its size in bytes, but here we have the value in bits. So you could multiply size of big-int chunks times 8, and then divide bit count by this, and this will give you the amount of full chunks. So the next thing you will need to do is to check whether there would be a residue from the division, and if so, then add one extra chunk in order to fit all the required data.
Okay. So would this here I'm not sure if this is going to be very valid. If I do
Yes, if you do.
Sorry, trying to think. If I use the residue and I get a 0 or any number above 1 in an if, is it going to give me like a valid true or false, or is it not gonna work?
Well,
Like for example,
so first of all, if you just divide, then you will just get something
yeah,
that will
it
tell
should
you,
be.
yeah. And that would work. If this is not 0, then it means that you need to add one more chunk to the array. But first thing you should do, of course, let's finish this line, and then we can think about the line that should go before this one.
Okay.
You need to take the size off from this, since you want to have the byte count of the type. Okay, and what is also needed is you need to multiply size of with 8, since we wanted to have it in bits, and for good measure put it in a bracket, since these are all operations of the same priority, so it would not do what we want if we don't use the brackets. Okay. Good. So this line will do what you want it to do, but we first need another line. So insert a line, a new line between those two. Create a new variable, chunk count.
Should I use size t or?
It's good practice to use size t for everything that contain sizes, but realistically we will not have more than 4 billion chunks, so it really doesn't matter.
Okay.
And assign, and now you want to have the count of full chunks. So
okay.
Let's try to fill this. You can copy the content of the if and just change one character. You could copy more.
This?
Well, what you just want to do is to divide bit count by a size of big in chunk times 8. So you can take the whole content and just replace the modulo operation with a normal division. Yep. Not, yeah. Strichpunkt. So this gives us now the count of full chunks. And if the if is true, then you need to add the line below it and increment chunk count by 1.
Okay. Or should I use the atomic addition, or?
No, that's fine. Okay, so now we have the chunk count. And the next thing to do will be to allocate the new data object for our int. So we have a function for it. It is called alloc data. We have implemented it if you scroll up to no, somewhere here. Yeah, we have the function, but as you see, the function takes the size in bytes. So what we need to do is to pass to it the chunk size, sorry, the chunk count multiplied by size of chunks.
Okay. So
It's complaining. complaining for a good reason. Something is missing.
Should be size of?
Yes. Okay. So now we have our data allocated, so we can start processing the string. So the next thing to do will be to create a loop that processes every character in our value string.
I guess we can. Would it be better to start at the beginning or at the end? Because if we start at the beginning, we can just like append stuff at the end, right? But
we cannot append because we only have one array, so we need to calculate the right offset either way. But it probably makes sense to start at the end of the string, so with the least significant byte, and then work our way upwards to the most significant byte. So let's process the string in reverse order.
So it should be from bit count, I think. -1.
Yeah. Yeah.
And 0.
And
then then let's see. Now, if I get the data from
the value, you can either use the square bracket operator, and I think it should have the .add function as well to get something at a offset. So just like with an array, you just write value, square bracket open, I close square bracket.
All right, very iterative. Well, here I was looking at the definition.
We will also be needing to fix oversight in the alloc data. Namely, we are not clearing it. So when it's allocated, it's full of random data, and it would be for us.
Use detach?
No.
Here.
We'll just go to the alloc data function, to its definition. Sorry, to its body, I mean. Yeah, here. And once we're done with a new begint, at line 52, insert a new line. And just use memset to fill the data structure with zeros.
Just 0?
No. It first takes the pointer to where it should write the 0, so it takes first the pointer to pdata. You forgot the arrow. Yep. Then it takes which value it should set and takes 0. And then it takes the size in bytes. So I think usize should be right. It's a big chunk. Yes, it's in bytes. Okay. So now we know that any allocated new big int will be full of zeros. That helps us. Because then we don't need to clear any excess bytes at the higher significancy bits. Now we can go down back to our function and continue. So here now what you need to do is to check whether the value is 0 or 1 or something else. So there are 3 cases: it's 0, it's 1, or it's neither. If it's neither, then just return false, because this means it's not a valid string. We just abort the operation. If it's 0, you don't need to do anything because it's already 0. But if it is 1, then you need to calculate the right offset and set the bit.
Can I use a switch? for that?
You don't need search. You have the character. You can just compare it.
Okay.
If you want to make it particularly cool, you could use a switch. So just write switch, open brackets, normal ones, round brackets. So the switch takes first of all a expression, and then you need to close this brackets after the thing, yeah. Then you can open and close curly brackets, and inside the curly brackets you can write different cases, so different values which value may have. Yeah. Case and no, it's not just 0, it's 0 in single quotation mark, since it has to be a character 0, not a 0 0. And also technically we have white characters, so we should prefix this with an L, but practically it's the same number, so it doesn't matter. Then double point, and since we don't do anything in this case, you just write break and a semicolon. And if you are inside the switch, the break only applies to the switch, so you cannot break out of a loop being inside the switch. Then you can write the default case, which means it's an invalid character.
Was it default?
Yes, just default double point. And then return false, so we just return from the whole function because something went wrong. At this point we could change the other return to return true, since if we arrive at the end of our if we arrived at the end and we didn't encounter any other characters, then it's fine. And now we also need to add the case for 1, so somewhere here, yeah, case good. And now the challenging part to find out where exactly to set the bit. So we need basically 2 indices, one denoting in which chunk we have to set it, and the other denoting in which exact offset within the chunk we need to set our bit. Also, I would recommend to open and close curly brackets, since you cannot define variables directly inside a case. You need to open and close the scope. Yeah, inside L1. Just open, close. No, is equals. No, sorry, is doppelpunkt. Sorry, I misspoke. Einfach Doppelpunkt, and then open, close curly brackets, so that you have a scope. And inside the scope you can then define variables, and it will not complain that a variable was skipped by label. And of course you need to add a break at the end, otherwise it will fall through to the default case. This is something that always needs to be kept in mind, that if you don't break in a case, the next case will automatically be invoked. So it is there are use cases where this is useful, but more often than not it is a cause of bugs, because people just forgot the break, and then the code is doing 2 things or doing unexpected things. So always keep in mind to do the break. And there are, like in, for example, C#, you cannot you still have to specify the break, but if you don't specify the break, it just says error and you cannot compile. So it's kind of they should have get rid of the break if you cannot not specify it, basically. But well, okay, so do you have any idea now how to find out at which indices we will need to set the bit?
So just a quick question. Is it possible in C++ to define the break outside the scope like this?
Yes.
In the case? Okay.
Yeah, you can use it on any loop, I think, right?
Break on for loops for sure. I'm trying to think. Maybe. I don't know about if statements. I haven't tried that. Probably.
I think in while.
Well, it's a switch statement. You cannot break out of an if statement. You can break out of a loop or out of a switch.
Yes. So while loops, for loops.
Yes.
Okay. Cool.
Can you use this this indice to find out which chunk it is, or?
Well, I already specifies the absolute bit count, but what we need to know is in which chunk. So,
so
that's quite easy. Just try to find a way. We kind of did something similar already in a way. It's very similar to finding out the chunk count. Just that instead of the total bit count, you need to use the current bit's absolute position. So our I variable.
So if I is larger than the well,
you don't
take
want
the
to
module of the big int chunk with divide.
A divide is a good start. Divide will give
yeah.
us the position in the absolute chunk.
Mm-hmm.
So let's try that.
So if I divide it by, so if I make this an int and divide it by I, isn't this going to give me, like, for example?
No, this is not going to work. You need to do something similar like in line 103.
Okay.
You can start by just copying line 103 and then adapting it. That's always a good start. Copying some code and then adapting it to do whatever you want it to do. Although in future people will probably be using AI to get the rough outline and then fixing whatever the AI screwed up. So this is going to change. What we need here, of course, we should call it not chunk count but chunk index, obviously. And we need one more change. Do you know what?
Is instead of bit count I?
Yes. So this should give us the chunk index which we want to access. And the next thing we want to know is the exact position within the chunk.
Okay.
You look at line 104.
Yes, we can use the module.
Yes, exactly.
Yep. Okay.
I would call it the bit index, or the chunk location is just fine. Chunk location is also good. A closing bracket is missing. Yeah. Okay. So that should be a good start. So now we need to get access the chunk out of our MP data. Sorry, M pointer arrow P data. To be correct.
And then
you can access it using the square bracket operator.
this?
Nope. Chunk index.
Oh, chunk index, yes.
Okay. And then we want to set a bit. Do you know how to set a bit? One single one.
I don't.
You use the OR equals operator.
Sorry, this.
Yeah, and that's the total OR. It's just a single vertical line. The double vertical lines or double ends are like logic operators on the whole expression. If you want a bitwise operation, you just use the single character and equals without a space. Okay, and now what we need is an object or a variable of type chunk, which will only have one bit set to 1. And the easiest way to achieve this is to just start with something that is 1 and then shift the bit to the right position. So just start with is equals 1 and then the left shift operator. That's the right shift operator, I think. This one. And then bit index. And semicolon. That should work. Let's try it out. You can go to the main function, main class, and then main file, and then to the main function. And then you can try to create a new big int. Just call it my big int 3.
We have a 3 maybe 4.
The space should not be there. And then you can call on this new object the from binary function. You can use the IntelliSense. If it shows you the list, you can click on one of them and then it auto completes. Yeah.
And then
first we need the function name.
Value.
We need the function name. From bin. And you could pass the string which we used in line 10. Just drop the 0b prefix. No, that's a integer. You want to copy the content of the thing and pass it as a white string. So L double quotation marks string L not okay, semicolon. And let's remove the 2 breakpoints in line 17 and 15. And what we also, now the one that return we would like to keep, and what we also should do is we could use the same function as in line 13 to print it to string again, and then see if we get the same result. Then we will know if it worked or if it failed. Yeah, just begin for. It's fine, you just need to add the 4 the right offset. Yep, okay. Let's run it. Okay. May I have the mouse? So let's see. Nope, we inverted everything. Invert. Well, that's progress. Wait, so first of all we print this here, so also let's print not here. A new line so that we can compare them better. And since we have inverted everything, we need to fix this. Do you have an idea how to fix this? It is reasonably easy.
I guess just starting the 4 at 0 and then counting up instead.
No, this will have the exact same result because we are calculating the offsets to insert it to.
Oh yeah, right.
You need to modify the offsets either for your for your chunk index and bit index, or you need to modify the offset in line 109 where you are getting the character from the string.
Yeah, I don't see it, sorry.
So the simplest way to fix it is just to revert the order in which we are retrieving this value. So we just take our max index minus I. This will just make us get the value from the opposite end of the string. Now if we run it, it should be working. You will see. Yes, it works.
Okay.
Perfect. Very good. Next candidate, next assignment. So, since we have already worked with some operators and we have some operators scheduled as homework, what might be a nice idea to take a look into would be implementing either the comparison operators or the bit shift operators. So, who wants to be next?
Should I disconnect?
Yes, please.
Hope that wasn't too painful.
It was okay. Well, if no one is volunteering, how about Mr. Kevin? Hello, Mr. Kevin, are you there?
I can try it, but I don't think that I'm gonna be able to pull it off.
Well, you can try. If you don't try, you don't know.
Yeah.
Okay, so let's go with the simpler of the things. We will be trying to implement all the various comparison operators. And the thing about those is that they pretty much all can be implemented as one-liners as long as we have a compare function which returns 3 different values depending on the status of the comparison. So for simplicity, let's just start with the compare function. I will make a prototype for it. So it returns int. It's called compare2, or it's called compare, whatever we want it to call, obviously. The name for it is I just call it compare. Is for us to pick. It is a const function because it is not changing the existing data, and when we go here we can create a body for it. So the way this function is supposed to work, let's quickly write it down. This So that's the general way how it is supposed to work. And since we are with our big ints in a regime where we have different sizes of our data, it is not as trivial as having, for example, a compare function for 2 integers, because 2 integers have the same size, so we only need to compare their payload. Here in our case, what we need to do is we need to somehow wie sagt man das auf Englisch, dem Rechnung tragen, somehow take into account that the two different data objects we have may have different sizes and a different count of chunks. So one option, one good strategy to implement the function is to first of all get the size of the larger of those two. Important thing to note here is that just from the size we cannot deduce, if we want a mathematically valid comparison, which one is bigger, because one might be like nominally bigger because it was initialized from a big number to begin with, but at the same time contain only a few lower order byte set, while another one, which was initialized from a smaller type of integer, might have a few higher byte set which are still higher in value than the lower ones. So we need to find a way to process always the whole thing, even if we have a size mismatch. So and since we care for which is bigger, we obviously will start the comparison from the higher order bits. And what we also can do is we can exploit the fact that our for our basic type, for our chunks, there is already a comparison. There are already comparison functions implemented in hardware. So basically, we just need to start comparing from the highest order chunk, and then compare every highest order chunk with the corresponding other highest order chunk. And if they are not equal, then we just look which one is bigger, and then we return 1 or -1. And to do that, I would recommend with first creating a variable which will contain the size in chunks of the bigger of the two objects. Then we will have a for loop which starts in reverse order from the highest order index, goes down to 0 including 0, and internally will retrieve the value of both chunks. And here I would use the trinary operator to check each time whether we can actually retrieve a chunk at this index, or whether that would exceed the size of our data, in which case we just assign the 0, and if we can retrieve, then we assign the actual value which can be retrieved. So I would recommend to start with creating a variable and filling it with the size of the bigger of the two objects.
So we want to compare the sizes of the digits first, or what?
Well, we want to compare pointer arrow usize with other pointer arrow usize to see which one is bigger, and then assign the bigger one to a temporary variable called, let's say usize. So we need to start by defining the variable first. I would also recommend to write the code below the comment which describes how the code is supposed to work. That's kind of, when you read a file from top to bottom, that's kind of the natural order of things. First you say what it's supposed to do, and then you have the implementation. You don't. Well, first let's start by creating a variable called usize of the type size t. That is not quite right. You have an example how to define a variable, for example, in line 113. You first write the type, then you write space, and then you write the name of the variable.
Oh yeah, okay. And what do we want to name it?
Well, usize. Usize will be the name. You have the wrong order. It should be like in the other lines, first the type, then the name. And I would use a capital S. It looks nicer.
Oh yeah.
Okay. And you can just initialize it with 0. And the next step will be to have an if, and then you can use normal built-in mathematical compare operations to compare the sizes of our two variables, of our two types.
So will we compare size t to usize, or what?
well, usize is for now empty. We leave usize in peace. What we want to compare is m pointer arrow usize with the same thing but from the other object. You need the arrow operator, not the dot, since it's a pointer. No. Underscore was fine. You need to replace the dot with the arrow.
Okay.
And it was an underscore, not a minus.
Mm-hmm.
Okay. Okay. That just checks whether it's not 0. You need a nope, it needs to be inside the brackets.
What? If this is smaller than 0?
No, we want to compare the usize of the pointer of the current object, so what we have staying here, with the usize from the other object. So the big int other, as defined in line 127, contains an own m pointer, which has an own usize, and we want to compare these two usizes with each other. That is very wrong. So on the right hand side of our comparison operator, of our less operator, you want to have your other object, then access the m pointer of the other object, and then access its usize variable. You can start by typing the name of the other object as defined in the only argument which our function takes.
Can you repeat that?
You can start by typing the name of the only argument our function takes. So our compare function defined in line 127 takes one argument of type big int.
Yeah, it only takes usize, right?
No, line 127. Int cbegint double point compare open bracket const cbegint and other close brackets const. We want the argument name other. Then since it's a reference, you can access it like a local variable. So we just put dot. And this gives you access to the inner variables, like the m pointer. And that one you can access like the other m pointer using the arrow operator, since it's a pointer, to access its child members, in this case usize. Yep. Good. Now you don't want a semicolon after your if, because that would make your if to nothing. And if we know that pointer size is less than other pointer size, then we can add here in the next line assign to our local usize the bigger of the two usizes which we have compared with each other. And you can just use the is equals, you don't need to write assign something to anything. It's very you can use mathematical equations a lot in C++. It's very, very nice.
So
usize equals and then the bigger of the two variables.
The bigger of the two.
Yes.
That should be other, right?
Yes. Yeah, semicolon. And now we also need the else case. So if the comparison is not true, then we want to assign the other variable. You don't need to write if again, you just can write else. Just else without anything. Just else, like in human language. If this, then that, else something else.
Oh wait.
Why?
Because you said that we want to compare.
Well, we already did the comparison in line 129. Now we only want to handle the case if the comparison was false. We don't need to redo the comparison. We already have the result of the comparison in the current state. Just press enter and write usize and then assign the other variable to it. Well, the other variable, the one which is smaller or equals. Well, no, in this case it's always smaller. The upper one is greater or equals, but in the greater case, equals case, we don't care which one we assign. Okay. Good. So now we have the chunk count. No, wait, where's the chunk count? I think it's just the byte count. What was our definition? Yeah, it was the byte count. We have a function called count, which gives us the amount of chunks a certain size represents. So you can write count, I think with a small c. We didn't make it capital for whatever reason. And you can pass to it usize. And assign the return value of count to a new variable called uCount. Nope. It's like in math, you write something and then it equals something else. If you want assignment. Nope. You need to pass one argument to the count function usize and then you close the brackets.
Oh God. I want to assign usign to uCount.
You want first of all to close the brackets after usize because you want to call the function with the right argument. Yeah, and assignment in C++ is done the same way as you did it in line 132. You just write the name of the new variable is equals whatever you want to assign it to. You don't need to use any more exotic yeah, but that's kind of the wrong way around. You want to assign something to uCount and not uCount to something. Nope. Go to the beginning of the line. First you write the type you want your new variable to have. Then you write space, then you write the name, and then you write equals. Okay, now we just need to prefix the whole thing with the right type before you count. Type space.
What's exactly missing?
You are missing size t space before you count.
Okay.
Before you count, not before count. Yeah, just replace the t with a z and that's that. No, you count is fine, don't touch you count. In the type you have a typo. You wrote site t, not size t.
Yeah.
Okay, and then you can close the line with a semicolon at the end. Okay, so we have the chunk count. The next thing we need is a loop that will go from chunk count -1 up to and including 0.
So something similar to this one?
Yes, very similar. Just instead, yeah?
So here I'm gonna take the MPTRU size and the other MPTRU size?
Nope, you will take u count. No. Int e was fine. You need to replace bit count.
To u count, right?
Yes. Okay. Then the function, then the for loop needs a scope, a body, and inside of this you will want to have two variables of type begin chunk, and to one you will assign the value of the begin chunk stored in one object, and to the other the value stored in the other object, so that you have the two chunks, the matching two chunks from the two different objects, and then you will be able to compare them directly. You don't need a switch. First you need to define the two variables which will hold the values of the two chunks to compare with each other.
Can you repeat that?
You need to define
Please.
two variables and assign one of them with the right chunk from MPTR-P data and the other one from other MPTR-P data at the same offset of E.
And I can name them however I want to?
Yes. Well, don't use special cases, just ASCII cases, numbers and underscore. a variable name should not start with a number, so you either you need to start with an underscore or with a letter, or just call them A and B or something like that, or value 1 and value 2, that's also fine. And of course you need to specify the type as well.
The type should be begin from.
Yes.
Right. Okay.
You need the space. Okay, that well, but as I said, we don't want users, we want the right chunk from the pdata array.
So pdata.
And then you need to specify the index, which chunk we want. Because our idea is to just take one out of it.
Is it also chunk index?
No, it's I. You only have the variables available which you have defined yourself. So if in this case we only have I, since it's called I in line 134.
Okay.
And semicolon, of course, at the end of each line. It was a double point.
Yeah.
Good. So now we will need to take also. Well, let's start with comparing. So now what you can do simply is you can compare whether A is larger than B or B is larger than A, and return the right values if any of these cases is encountered. So the loop will run only as long as they are equal. As soon as one of them is not longer equal, then the loop will terminate, either returning 1 or -1. And if the loop runs till the end without termination, then it returns 0, because it means that we have not found any mismatch.
So we compare the digit sizes of A and B.
We compare just the value of A and B. You don't need to write value. A and B are just already values. You can just use them directly. Yeah, if A is less than B, then you need to return one value. The semicolon after the if should go away, otherwise the return will always be triggered. Yep. You don't want else, because else may also include the they are equal case. In this case you want to make another comparison the other way around, and then return -1. Okay, and last thing to do is, after the loop, if we haven't returned already, we need to return 0 in order to ensure that all the branches in our program will return a value.
Can you repeat that, please?
You already had a closing bracket. You have now 2. That's one too much. You just need to return 0 after the loop, since we always need to return a value. No, we are inside the loop. You want to do it outside the loop. After the closing brackets from line 143. Okay, well, you have still 2 closing brackets, so may I have the mouse?
I don't need this one down here.
Yeah. Yeah. Okay, that, well, the function, the implementation doesn't have any safeguards of any kind, but we could try whether that works. The safeguards and so on we will add later. Can you make a test case for it in the main CPP?
If I can make a test case in main CPP.
Yes, so you can create two different big int objects with 2 values, and then on one of them call the compare function and pass the other one as an argument. It's called cbigint to be exact.
And I just give it a new name, like my
just give it a new
5.
name, yeah, for example, exactly. Function is called compare. The IntelliSense was actually showing you the available functions so that you could pick from them. It would be good to first define a bigint 6. You don't need from I think we made it such that you can assign values in the constructor. So you can write in line 22 after the bigint 5 or opening brackets, and then just a number, an integer number. Let's say 5 before the semicolon, of course.
Yeah. And then I define as.
And then you define a bigint 6. You can give it the value 6, for example. Why not?
And then I compare those two.
Using the compare function, yes. You are passing a bigint 6 to the compare, and you should store the result in a variable so that we see what was returned.
I like this.
Yep, just store the return value in a new variable of type int.
How do I do that?
Yeah. You did that already once, or actually twice or 3 times in your order. You just write the type of the variable, then the name, and then the equals sign. For example, like in line 128. Just go. Don't copy it. Just write int space, then a name, let's say red, and then equals sign. And of course before your function. Like in math, you write the thing you want to assign a function to before you write the function. Just move it, the whole thing, the whole content of line 25, move it to the beginning of line 24.
Oh, to the beginning of 24.
Yes. Okay, and let's play, press play. Yeah, this one. Okay, may I have the mouse?
Yeah.
So let's see. It returned 1. Fair enough. If we put 4 here, it should return -1. And it did. And if we put 5, it should return 0, because then they're same. Now whether 1 and -1 are correct or whether they should be swapped, we should find out, but this is a second order problem. Okay, so before we continue with that, so thank you for your participation, and that was okay-ish. Let's take a look into improving the function, because there are a few things that need to be taken into account when working. First of all, MPTR, I'm not sure whether it's always existing. No, it's not. So MPTR might be null, so we need to check that. So for example, you can create 2 variables, L size, which will then check if this variable exists, then it is size, and if it doesn't exist, it is 0. This line is equivalent to having just this, and then if this is, so this line does the same thing as those however many 5 lines. It is the trinary operator, which is quite a nice thing, and of course in C++ new lines don't matter, so we can just make one line out of the other version as well. But let's continue. I call it L for left and R for right, because usually when you make compare operations, you call the left and right operand. And here we do the same thing for R size. So now we know that if this does not exist, it will return 0 automatically. So now we replace here our pointer size with L size, and the other one with R size. So this way we are not risking accessing a MPTR which would be null. That would not be good. That would be very bad. That would crash our application. And then here inside our for loop we have a similar issue, namely that the index may actually be greater than the amount of elements in our pdata array, at least for one of the 2 things. So what we do is, again, we use the trinary operator. So we check if usize is less than I. So if it's less than I, then it is if it's greater, it must be greater than I. If it is greater than I, then we are allowed to access the element, and the element exists. And else, if it's smaller than I or equals I, then we return 0, because there is no chunk at this position at all. And then we just repeat the whole thing, just that we use the other. And for completeness, I would rename those to left one and right one. I was left, right, left, right. So we want to keep the nomenclature, so to say, intact. And one thing we could do would be to access those by reference, but I think this doesn't matter. It will not be any faster. So now we can also compare things which will have different sizes of chunks in them, and we'll be also able to handle the case when we compare it to a variable which does not contain anything. Good. So that's that. We have 6 minutes spare, so we should think about some homework assignment. Since we already assigned you multiply, divide, and so on, we will assign something new. Do we? Yeah, this one's homework from the which day is today, 19. TL due date will be the 13th. Oops. And add and subtract. So like with those, we just want to implement those two functions. Here we have one less. And yeah, when you implement this, you of course have to take it is much easier than the multiply and divide thing is. What you need to take into account simply is that you will have when adding or subtracting chunks either an under or an overflow, and then you need to carry over the remaining part of the number to the next or previous chunk. Well, usually always to the next chunk. So this is something to keep in mind. It's not as simple as just add the chunks together and you're done. No, you always have the overflow, and you need case, and then you need to carry the remainder to the next chunk or borrow it from the next chunk in case of a subtraction. What would probably be nice just for completeness, since we are subtracting, to add also a function to invert, to make the negative. So let's add this to the homework as well. So add, comma, subtract, and swap sign. So what swap sign does is basically just it returns you a, as the name says, a copy of the number just with the opposite sign. The opposite sign. That of course assumes that we want to, that our big int supports signed numbers, which we might not necessarily want. I think for now, maybe for simplicity, let's just stick to it being unsigned. So let's ignore that case. If the thing works, if everything works out, then we can look for other assignments. And one last thing we should do, since we started this compare function, we should write the right operators so that we have so that we can use mathematical operators on it. So ball operator less than the operator itself is const, and we return compare other, and then depending whether we had the right or wrong, either equals 0 or bigger than 0. We will just try it out and see which one works correctly. So the other operator, oops, goes of course here in the other direction. Then we can have of course an operator for is equals. Oops, is equals. So of course it must then be equals 0. And in principle the other operators can either be, and all the other can be implemented quite similarly. So here we go to is lower equals greater equals, which just means this, and then we go lastly at the not equals operator, where we just compare whether it's not 0. And now let's quickly test whether the return values in our function here at the bottom are right, or whether they need to be swapped. So we assign let's say 5 and 6 again, and then instead of this we make if 5 is less than 6, which should be the case, then let's say return 1, and else return 0, and then we see in which case we fall. If we fall into the return case, then we know we need to swap the, yeah, it was the wrong way around. So we need to swap the return values in our big int function, sorry, in our compare function. And now we have the right case. So voila, our compare function works as expected, and our operators are all implemented. This is actually quite nice of a implementation method, because you can implement all 6 available comparison operators just with one function, and then just checking which return value we've got. Okay, since we are running out of time right now, are there any questions?
I just have one question about implementing the multiplication. When we do it, should we assume that the number stored is binary, or?
Well, the number stored is stored in our chunks as integer parts.
Okay.
So it's not binary in the sense that it's a string of zeros and ones. It's binary in the sense that it is really represented by an integer type inside our chunk array.
Okay.
Any other questions? Okay, if there are no more questions, then we are done with the exercise. We will continue in 2 weeks from now, since there is a holiday next week. So have a nice weekend. Bye bye.
Thank you. Have a nice weekend.
Thank you. Bye bye.
Have a nice weekend.